All right, so thanks for coming. Our next speaker is Keeler Spear. He's going to be talking about modeling transmission lines.
Hello everyone, I'm Keeler Spear. I'm a current student at the Metropolitan State University of Denver, Colorado Early Colleges, Douglas County North, and a former student of Arapahoe Community College. Today I'll just be going over how to model transmission lines and a numerical scheme to solve them more efficiently. Right, so today I'll just be going over the equations themselves, the initial boundary value problem, and a toy problem I found to test the scheme on, how we can derive the method, the stability analysis, how to implement it in MATLAB, and then the results. Okay, so just starting with the equation, we have for the Telegrapher's equations are a set of coupled first order PDEs for voltage and current. The constants in there are the resistance, inductance, the conductance, and the capacitance. These will all be in SI units. The resistance will be in ohms per meter, the inductance will be in henries per meter, the conductance will be in Siemens per meter, or just 1 per ohm meter, and then finally the capacitance will be 1 farad per meter. Now this system is great and all, except it's very difficult to model numerically, so I'll want to decouple them. So first, to just start that off, I'll take the partial derivative with respect to space on the first equation, and then the partial derivative with respect to time on the second equation. This yields this system above, and then from here you'll notice that you can easily plug the second one into the first one, and vice versa. So using that, we can create this new system, and then after simplifying it, we get the bottom one, which is pretty long, but then we can again simplify that even further to get this, which is two hyperbolic second order PDEs, which will model the voltage and current independently of one another. Now, what's interesting about this is that if we take the line to be lossless, so the resistance and conductance are 0, we'll get the wave equation. Of course, transmission lines are not lossless. We have to have all that extra stuff in there. That's just one interesting thing to note about these equations, how similar they are to the wave equations. So with this all set up, we can take a look at the IB, the initial boundary value problem we seek to solve. So this is a toy problem with a resistance of 500 ohms per meter, an inductance of 1 henry per meter, capacitance of 0.1 farads per meter, and a conductance of 1 ohm meter, of 1 over an ohm meter. And this would never be a real thing. Hopefully no one ever designs a transmission line like this. It's just a problem curated so we can model it efficiently and get a graph, since the scheme later explored is very unstable and it won't work out that well for a real transmission line. So we do have a homogeneous initial condition. We're starting with the transmission line without any loss, and then the direction boundary conditions. We have a simple sinusoidal voltage connected to the left side, and then a voltage sink on the right side. So again, it's a test problem, so the initial condition on the left side, that's just sine of pi t, and the real world would be sine of 120 pi t. That's extremely unstable. My computer cannot handle doing that, so it's very dumbed down so MATLAB can actually do things with it. And I'll be looking at this over the course of 10 seconds, and the length of the transmission line will be 0.1 meters. That may seem short, but because of that really high resistance, the voltage dies off very quickly. All right, so moving to derive the method, we'll just take a look at the equation. So of course we have the two second order partials and 1 first order partial. I'll be replacing the second order partial with respect to space with a second order centered space differentiation scheme. The second order partial derivative with respect to time will be replaced with a second order centered difference time scheme. And then finally, for that last derivative hanging out over there, I'll replace with the first ordered centered time scheme. So what that will look like is, here's a slide of all those schemes. And just for the simplicity later on, these primary line parameters, the RC and GL, those get so messy later on, so it's just replacing those with some simplified constants. So an alpha equal to inductance times capacitance, a beta equal to the resistance times capacitance plus the conductance times inductance, and a gamma equal to the conductance times resistance. Then on the right, those are just some basic differentiation schemes. They all have an error of their time step squared, so h squared for the space derivatives and k squared for the time derivatives. So with these values, you can just plug it into the second order PDE for voltage. So here's that's what it looks like on the top. Still pretty messy. We want to solve for the next time step with the voltage. So that's what's happening here. I first separated it out, moved all the voltages with the next time step to the left side, and moved everything else to the right side. We still have some of those coefficients hanging out like the alpha and beta, so just factoring that out and dividing by it, we get this bottom equation. That's still really messy, and this is with the simplified coefficients. So when we just again simplify it, separating out all the voltages into simple categories and then reintroducing the primary line constraints, we get this mess. It's not very pretty, and it's a pain to run, but it'll get the job done, and it'll be more accurate than the forward time or backward time models. Okay, so from here, as nice as it would be to just immediately plug this into MATLAB and run it, we have to do some stability analysis. So from here, let's see. I will be simplifying the coefficients once again into delta, epsilon, mu, and rho, because it'd be impossible to do if you're using all those variables. I have to condense it here. And we get a really nice looking numerical scheme. It's just a few simple variables condensed into a pretty simple formula, not that bad. But then we get into the horrific stability analysis. So to analyze, I'll be using von Neumann stability analysis. I'll represent each voltage point with a discrete Fourier transform on the interval of -pi to pi. And if we just plug this into our scheme, which is shown on the bottom here, we get another really horrific looking equation. But fortunately, since all the integrands, or all the bounds of integration are the same, and the integration variable are the same, we can combine them into this equation. Not too bad again, although still pretty messy, so we can continue to simplify it by factoring out the complex exponential, which will yield the middle equation on screen. And then finally, moving on to the bottom one, that's just separating out the Vn hats and the n-1 hats. From here, we can then generalize it into a simpler equation of Vn+1 hat plus that entire thing. Again, we still have those complex exponentials, which is not ideal. So we want to replace them with their sine and cosine form. And upon doing that, it simplifies those complex ones into 2 rho cosine of h times omega. Now, this introduces another problem. Since it's not a simple or it's not a scheme with just a previous time step, we have 2. We can't just check the magnitude of the coefficient on it. We have to check both. So to do this, we have to convert it into a matrix equation. That will just simply take the form of the next time step is equal to a matrix times the multiplied by the current time step. So that's simple to break up. You just create that matrix there with a 0, 1 delta mu and delta epsilon plus 2 delta rho cosine of h omega. And then from here, the thing we want to look at is the eigenvalues of it. Since if they have a magnitude less than 1, that means the system will be stable. So we start by subtracting lambda I from the matrix there. So we get this bottom equation. And then once we take the determinant of it, we get a nice little characteristic equation at the top. And then we can again simplify that into a nice quadratic. Now, since it is just an order 2 quadratic, we have a nice 2 by 2 matrix, we can plug it into the quadratic equation, yielding the bottom results, which is still pretty messy, but it's manageable. We'll be able to evaluate it. So if we want to finally, this final one, plug in the first layer of constants, which were replaced before, we get the top equation, which is messy, but then it gets worse with the bottom equation, which is so compact it doesn't even seem to be loading onto the projector correctly. But that's what you would have if you didn't want to deal with all the layers. You just want to plug in the line coefficients, your time step, and your space step. And again, for this, we want the magnitude of it to be less than 1. So if we just plug that into the inequality, we get this. It's took more than one line to put it into the slide, but there it is. So as long as that eigenvalue is less than 1, the system will be stable and it won't get crazy looking graphs or anything like that. Right, since we now know that the implementation will be stable and all of that, if it meets that condition, I've implemented it in MATLAB. I would have preferred to do another coding language, but MATLAB is what I have. Okay, so first off, it's a simple function. You just give it the primary line constraints, the L, C, R, and G, the length of the transmission line, the amount of time you want to run it for, the initial voltage, which is the next time step, the boundary conditions, and the time steps. And at the beginning, this is just simplifying a bunch of variables, because later on, if we're doing a double for loop, we don't want to be doing h squared that many times over and over again. So for computational efficiency, all of these have been simplified. So here is a quick stability check. It just checks every possible case of the eigenvalues. So with that cosine theta, it checks when it's -1, 0, and 1, and it checks the plus and minus for each case. If it does detect that the eigenvalue is greater than 1, it throws an exception. I don't want my computer exploding trying to run this, so that's a bit of safety added into there. Then this is setting up the matrix, so we just have, first we're just creating the x and t vectors. That's when we plot it, we get accurate measurements. We can see the time and meter distance along where the voltages are at. We add the initial conditions to the first and second rows. Now in this problem, since we have a homogeneous initial condition, it's just 0 once again in the next one. Otherwise, if you wanted to have a non-homogeneous initial condition, you'd have to do a Taylor series expansion to find that via xk. And then finally, we add in the boundary conditions to the matrix. So here's just adding in the left column and the right column with all those values. So again, in the IBVP I showed, the left column will just be the sign values and the right column will all be zeros. Finally, from here, we actually implement the numerical method using those simplified variables for computational efficiency. It's a double for loop, so ignoring the rows we've already filled in, it just goes matrix entry by matrix entry, doing all of that. And once we do all of that, you get a solution and graphs, assuming your system is stable. So, moving on to the results for the initial boundary value problem. Here's just a quick reminder of it. We have the really high voltage, so that's why the graphs are going to look nice, because we don't have to do modeling anything crazy. And then specifically, the h is 0.01 and the k is 0.001 for the times all those steps. That does provide enough stability, and once you run it on the code, we get these two graphs. So as you can see, there's the nice sinusoidal on the right at any time with the position of 0, since that's the left boundary condition, and that's just looks really nice. And then on the right, 0. So because of all the really high resistance in the transmission line, it just dies out almost immediately. If you were modeling the real one and you had a sufficiently strong computer and it was stable, it'd be just constant sinusoidal peaks. But here again, it's a nice clean problem that dies off quickly. So if we want to look at the stability of this system, we get a lambda of 0.9901, which is less than 1, so that's why we get those nice graphs. If it was greater than 1, either MATLAB would crash if I ignored all the error throwing, or it would just give me basically a block of a graph, since it's so unstable. Then in terms of efficiency, I've ran this code around 30,000 times on the average, and it can execute in around 0.0015 seconds, which is pretty good. And then error-wise, I did not find an analytical solution to that yet, since I'm unexperienced in the area of analytical partial differential equations. But because we're using all those O of h squared and O of k squared errors, it should be on the magnitude of the step size squared. So that about wraps it up. Here is a code to the GitHub, or a QR code to the GitHub, which has all the code used, including a basic main executable function, and then all the boundary initial conditions. And that's it.
All right. Let's thank you.